So now let's talk about continuity on a closed interval. So you might want to kind of have a picture in mind of a function. So let's just look at a graph here of some kind of function here from A to B. And I'm only looking between, on this closed interval from A to B. So I'm only focusing my attention in between these two, but I'm also including my endpoint. And so I can say that f is continuous on this interval A to B if the following three things happen. So the first one, your function needs to be continuous inside of the interval. F is continuous on the interval A to B. So in the middle here, my function needs to be continuous. Now, the difference between an open interval and a closed interval is that I'm including these endpoints. So I have this first endpoint right here, which is going to give me my second condition. Because I'm only looking in that interval, I only have a right-handed limit. So here the condition is the limit as x goes to a from the right has to be the same thing as f of a. Inside of that interval, I only have numbers on the right of a. I don't have anything to the left of a. And then you're going to have a similar condition for this other endpoint, but now it's going to be a left-handed limit. So the third condition is that the limit as x goes to b from the left is equal to f of b. So let's look at an example here. Let's discuss the continuity of the function square root 1 minus x squared. So I'm going to start by focusing my attention on the domain. What is the domain of this function? Well, I can only plug in numbers between -1 and 1, including those two values, because otherwise I'll be taking a square root of a negative number. And we've looked at a similar kind of function previously. If I graph this function, it would be the upper half of a circle of radius 1 centered at the origin. And if I look between -1 to 1, my function is continuous. So I know that it's continuous on -1 to 1. And this corresponds to that first condition in our definition. So now I've got to take my one-sided limits of my endpoints of my interval. So let's start with this one over here. I'm taking the limit as x goes to -1 from the right. And what would the limit be as I approach from the right? My y values are getting closer and closer to 0. And this is also the same thing as plugging in -1 into my function. So I notice that these are the same. They're equal. That was the second condition I needed to check. And now we're going to look at our other endpoint, the limit as x goes to 1 from the left. So look at my graph as I approach 1 from the left. My y values are getting closer and closer to 0. And this is the same thing I get as plugging in 1 into my function. These are the same, they are equal. you could say. And so now I can conclude that my function f of x is continuous on the whole interval -1 to 1. So now let's talk about some properties of continuity. So here I'm going to assume if b is a real number, so b is just a scalar, and f and g are continuous at x equals c, then these functions are also continuous at x equals c. So I can take a scalar multiple, b times f. A second one, I can take a sum or a difference. I can add two functions together or subtract them. I can multiply two continuous functions together. It would still be continuous, so you can take a product, f times g. And the fourth and final one is a quotient, but there is a condition on a quotient. You need to make sure that the denominator, that g of c, is not 0. And so this is kind of nice because now we've been looking at really simple functions, but now I can look at more complicated functions together. So, for example, I know that the function x, this is just a line, is continuous everywhere. Also, the function e to the x is continuous everywhere. And what I can do now is I can add these two functions together. Or sorry, this shouldn't be f, this should be g. I can now take these two functions and add them together, and it would still be a continuous function. It is also continuous everywhere. I can also take scalar multiples. So for example, let's just take our g of x, which was e to the x, is continuous everywhere. If I take 3 times that, so I'll call this new function I'll call it h of x. This is different than the previous example. I can take 3 times that function. This is also continuous everywhere.